Hey Royals, in today's lesson, we're going to look at frictional forces. So friction's a term that describes contact forces between two surfaces, and the contact force is parallel to the surfaces that we're considering. Now, just one point here that the surface might actually be a fluid, and we'll talk about what we mean by frictional forces with fluids a little bit later in today's lesson. Okay, so friction's extremely important in our everyday lives. It wouldn't, if we were to have no friction, we would not be able to walk, sit in a chair, or do pretty much everything that we do on a daily basis. Okay, so where does friction come from? So if you look at an object and you look at it on a macroscopic level, the surface, no matter how smooth you think it is in fact not that smooth. It has high points and low points, and that's what's shown here on the right-hand side of our screen. And so if I take, say, a notebook, and this is my notebook here, and I tilt it, and the notebook is fairly smooth, and I have a calculator, which again is fairly smooth, and I place them on top of each other. This calculator will just simply slide right off of my notebook. But however, you can hear it sliding. So that is our frictional forces creating sound here, sound energy. However, if I take my stapler here and I place it on top, it doesn't slide. Why? Right? There's more friction between this surface that's rubberized and my notebook versus my calculator, which is plastic, and my notebook. So on a macroscopic level, and I'll just zoom in on that picture there, you can see when these two high points of the surfaces make contact with each other, they essentially lock into each other and create a resistive force. And that is what causes our friction. It's the high points of the two surfaces contacting each other and making it harder for the objects to slide. So if you think about ice versus concrete, or I don't know, carpet has a lot more high and low points than a sheet of ice. And that's why objects seem to slide a lot easier on a sheet of ice versus across your carpet, right? Because there's now fewer high points on a sheet of ice than there is on your carpet. So there's different types of friction. For our course, we're going to focus mostly on that first one there, sliding friction. So sliding friction is present when we have two objects that we are trying to slide across each other. So if you rub your hands together, that's sliding friction. Rolling friction occurs with your car wheels. As they roll along, it allows that wheel to roll along and your car to move along the road. And then the last one there, fluid friction, which occurs with fluids. So that's your aerodynamics, your swimming outfits. If you're a speed cyclist, the type of uniforms that you wear for that are for reducing this fluid friction. It allows us to move through fluids a lot easier. Okay, so sliding friction. When I slide two objects together, so if you remember my stapler and my pencil, or sorry, my notebook, the stapler will sit here and it will stay stationary, static friction, unless I get it to a point where it overcomes the static friction. So I apply a force on it to cause it to start to slide. So you can see there, if I help it by pushing a little bit, I'm overcoming this static friction, which holds it still, to a point where it is allowed to move. And the moment it moves, it turns into kinetic friction. So there's a upper limit of what the contact between the two objects can withstand before we start to see some type of motion. So looking at it as a graph, essentially, you have your frictional force. If I put it on my vertical axis and I put my applied force on my horizontal axis, the frictional force, which I'm trying to show here, will match the applied force up to a certain point. So it will be essentially a straight line up to a certain point where the applied force and the frictional force equal each other. However, there will be a point when it gets to our limiting static friction where the object can't hold on any longer. And then it's going to drop down to a constant value. If I can draw it straight across, there we go. It's constant value where we get our kinetic friction. So I'll write this as F, and I'll write kinetic. And then at this point here, this is what we'll call the frictional force, but we'll call it static. Okay, and then you have your limiting static friction at the very top of that graph there. So I have a little applet to show us exactly what I mean by this. And again, I'm going to use the PhET online simulations. So in this simulation, I'm going to show you exactly what I mean by static friction. I'll show you the limiting static friction as well as our kinetic friction. Okay, so let's go take a look at that app. So let's investigate what we mean by limiting static friction versus kinetic friction. So in this simulation, we have a crash test dummy pushing on a box. And right now, they're not actually touching the box, so they cannot possibly be applying a force on it. However, if I allow them to push 50 newtons on the box, you can see that the frictional force is going to equate it, but in the opposite direction, which adds the forces together to give us a sum of 0. And that means that the object will stay at rest based off of Newton's first law. There's no net force on the object, therefore if it's at rest, it will stay at rest. So let's add another 50 newtons to it. And you'll see that the frictional force, in fact, also increased by 50 newtons. And the object is still at rest. So let's start applying forces just 1 newton at a time. And we can see that we can continue moving on, and the force is getting larger that I'm applying, and the frictional force is equating it, but in the opposite direction. And so let's get up to about 125. You can see that, again, it's not moving. But as soon as I get to 126, I break what we know as the limiting static friction. So we've reached the maximum that this box and its surface can withstand as an applied force. And the moment you go beyond that, watch what happens to the frictional force. Frictional force dropped to 94, and I now have a sum of forces equaling 32 newtons towards the right. And my box is starting to accelerate because I now have a net force acting on this box. So let's quickly run down to 94 newtons. So we can see that our newtons are dropping, 94 here. You can see that if I meet it at 94, the applied force and the frictional force are equal, my box is moving at a constant rate, which again agrees with Newton's first law. So if there is no net force acting on the object and it's in motion, it will remain in motion. What happens if I start decreasing the applied force? So I'm still applying a force forward on the box of, say, 65 newtons. But you can see that the sum of the forces adds to be 29 newtons towards the left, or backwards in this picture. The frictional force stayed at 94. So what happens is when the object is in motion, kinetic friction will remain constant at a certain value. And you can see here that it will stay at 65 once it's stopped. And I can start applying my forces again. And the static friction, because it's stationary, starts matching up to that limiting static friction value, which for this case of this box is 125 newtons. So I know that if I get to 125, it's going to stay stationary, but the moment I go to 126, I've crossed that barrier. So this is the difference between static friction, it equals the applied force up to the limiting static friction point, and then beyond that, you get kinetic friction, which remains constant at the value of the interaction between the two surfaces. So in this case, it's 94 newtons. Okay, so I hope this helped us out with our understanding of the difference between static friction and limiting static friction, as well as kinetic friction. So let's head back to the lesson to learn how we represent it algebraically. So welcome back. So what two things about the object cause this friction? So you might think, well, the type of material, you'd be totally right. So the bottom of my stapler was rubberized versus the bottom of my calculator was plastic. So the type of material definitely influences the type of friction or the amount of friction. So type of materials. And that will lead to something that we call the coefficient of friction. And then in physics, the symbol for that comes again from the Greeks, and it's called mu. It looks like a U, but it has kind of like a tail on the front of it. Okay, so the types of material will dictate this coefficient of friction. And there's coefficients of frictions for static objects, so the objects are not moving, as well as coefficients of friction for our motion, when the object starts to move. Okay, so another thing that might cause the frictional forces to change would be the mass of the object. So the mass of our object definitely will influence the amount of friction available. So if you think of like a rubberized shoe and it has the tread across the bottom of it, if I were to put 1 gram of mass on it, it wouldn't really have much friction. It would be easy to slide around on a concrete floor. But if I put like a 45 kilogram plate from the fitness center onto that shoe, it would have a lot more friction, and that's because I'm actually introducing more high points. I'm stressing that rubber to push it down into the concrete to create more connection points. And when I do that, I increase the friction on the object. So the mass is really important, and that will lead to an increased normal force. And so these two aspects will be important when it comes down to the magnitude of our friction. So the expressions for these, we can actually write them as algebraic representations. So frictional force, and I'll call it Fk for kinetic friction, can be written in magnitude as the product of our coefficient of friction for kinetic friction. So I'll use mu and a subscript k to represent that is kinetic friction, and it's multiplied by the magnitude of the normal force. And similarly, for static friction, we can write it as mu s, so the coefficient of friction for stationary or static objects, multiplied again by the normal force. So you can see that the equation for friction is very similar, and the only major difference comes from our coefficients of friction. And the coefficients of frictions are always constant depending on what two materials are in contact with each other. Okay, so let's use these in some sample problems. Our first sample problem here says that we have a wooden box that has a mass of 12.2 kilograms, and it's sliding across a horizontal surface. So the minute it's sliding, we know that we're dealing with kinetic friction. It's at a constant velocity, which means my acceleration is 0 meters a second squared, and that's being applied by an applied force of 53 newtons. So let's go ahead and draw ourselves a free body diagram of the scenario. So I have a box here. It has a gravitational force acting downwards on it. Let's get it straight down. So there's my straight down gravitational force. I have a normal force, which should be roughly the same length acting upwards. So we'll draw that as my normal force, my gravitational force. And then I have a applied force. It doesn't tell us which direction, so I'm going to say my applied force is towards the right here, and my frictional force is towards the left. And those should be roughly the same length as well, because I have an acceleration of 0 in the x direction. And when it's sliding across the surface of the table, it's not accelerating. Okay, so there's my situation. Let's go ahead and determine what is this coefficient of friction for the motion of the friction between these surfaces, the wooden box and the horizontal surface. So for that, I need to find mu k. And if I look at my equation here, I need to determine both the normal force and the frictional force. Okay, so let's go ahead and determine the frictional force first. So I'm going to say find Fk. Okay, so if I think about my horizontal forces, so my net force in the horizontal direction is equal to the mass times the acceleration in the x direction. Well, the acceleration in the x direction is 0. So I can say my net force in the x direction is the mass multiplied by 0, which tells me that I get 0. The net forces will be my applied force, which acts towards the right, plus my frictional force, which acts towards the left, is equal to 0. When I rearrange this, I find out that my applied force towards the right is equal to the negative of my kinetic force, kinetic friction force towards the left, and we know that that's not nice. We don't want negative direction, so the applied force is equal to the kinetic force if they're both acting towards the right here. So I know the applied force is equal to my kinetic force, and I've been told my applied force is 53 newtons. So that tells me that my kinetic friction force is 53 newtons. So I need that piece. I'm now up to the point where I know my kinetic friction. Let's find the normal force. So my second step here is find Fn. Okay, so let's go ahead and find Fn. And I'm going to go to my vertical direction to find Fn. So I'm going to say F net in the y direction is equal to the mass times the acceleration in the y direction. My net forces in the y direction is going to be my normal force acting up, my gravity force acting down, and my acceleration again is 0 because the object is not accelerating off of the surface or into the surface. So this acceleration piece is 0, so it comes out to 0. The net forces are acting to 0, which tells me my normal force is equal to, the normal force acting upwards is equal to the negative of the gravitational force acting downwards. In magnitude, that tells me that the normal force is equal to the gravitational force. And we know from a previous lesson that I can calculate the gravitational force as the mass multiplied by the gravitational field intensity, which tells me that my normal force is equal to the mass 12.2 kilograms multiplied by 9.8 meters per second squared. And that, if we work that through, gives me a force of 119.56 newtons. So I now know the kinetic friction force, I know the normal force, which will allow me to find mu k. So I'm going to say find mu k. So here we go. Let's find that mu k. So I'm going to say Fk is equal to mu k multiplied by Fn. Fk was 53 newtons. That's going to be equal to mu k multiplied by my normal force was 119.56 newtons. I'm going to divide both sides by the 119.56. So I get 53 newtons divided by 119.56 newtons. It's equal to mu k. And I notice that 53 newtons divided by 119.56 newtons, my newtons units will divide to 1, which is very important in this case to let me know that my coefficients of friction have no units. So there's my coefficient of friction in this case for this problem of 0.44. It should also be noted that the coefficient of friction should always be less than 1. Okay, so if you get a value that's larger than 1, that means that we have a numerical mistake somewhere in our problem. So definitely double check your work if you are getting a value larger than 1. Okay, so let's look at one more problem here together. So this is an applied force of 25 newtons west acts on a 2.0 kilogram box on a table. The coefficient of kinetic friction between the brick and the table is 0.57, and I want to find the acceleration of the box. All right, so let's go ahead and draw ourselves a free body diagram of what's going on. So I have a box here, and I know that I have a force that is acting westward. That's going to be my applied force. So my applied force is, what was it told to me as? 25 newtons, and it's west. I have, in this case, a frictional force. We don't know if it's larger or smaller, but it is moving. So we have a kinetic friction force because we were asked to find the acceleration. That means that it must be moving, which is going to act towards the east. I have a gravity force acting down. I have a normal force acting up. We'll put little arrowheads on this. So I have a normal force acting up, a gravity force acting downwards. And those arrows should be the same length. So I'm just going to fix my gravity one, just so that they are roughly the same length. There we go. So that will allow me to find the net forces in each of the directions. So let's start with the vertical direction. So I'm going to say find Fn. And I'm doing that simply because I know that my frictional equation has a Fn built into it, a normal force built into it. So let's say that the net force in the y direction is equal to the mass multiplied by the y direction's acceleration. And again, because this box is not accelerating vertically, that term's becoming 0. So if I look at my net forces, I have the normal force acting upwards plus the gravitational force acting downwards is equal to 0, because again, acceleration is 0, which tells me that my normal force acting upwards is equal to the negative of my gravitational force acting downwards. If I make them both pointing upwards, it tells me that my normal force is equal to my gravitational force in magnitude, which means that my normal force I can calculate. I'm told that it's a 2.0 kilogram box, so I'm going to use the fact that it's the mass multiplied by the gravitational field intensity. It's 2.0 kilograms multiplied by 9.8 meters per second squared tells me that the magnitude of my normal force is 19.6 newtons. All right, so we now know the normal force. We know the coefficient of friction between the box, or so the brick and the table is 0.57. And let's look at the net forces in the x direction. So let's find the net force, or let's go right ahead and find the acceleration. The acceleration is equal to unknown. Let's go ahead and find it. So I'm going to say F net x is equal to the mass of the object multiplied by the acceleration in the x direction. My net force is in the x direction. I'm going to say I have the applied force, which is acting westward, which in this case is left. So we'll say west, left, plus a kinetic friction, which we're not really sure what direction it's acting, but because it's opposing the motion, it's going to be acting towards the east. And that's going to be equal to the mass multiplied by the acceleration in the x direction. Okay, so the applied force. Well, I need to find the frictional force first. So I'm going to scooch down here. I'm going to say 3, find F K. And that will actually be, this will be my third step then. I'm going to abandon that one to find my kinetic friction. So let's go ahead and find the kinetic friction. So kinetic friction is equal to mu k multiplied by Fn. Fk is going to be 0.57 multiplied by 19.6 newtons, which tells me that I get a value of 11.172 newtons. Now I know what the magnitude of my kinetic friction is. Let's go back to find my acceleration. So my applied force was 25 newtons and it was west. I'm going to say subtract the 11.172 newtons west, because I've flipped the east with west, which is equal to 2.0 acceleration in the x direction. 2.0 kilograms multiplied by my acceleration in the x direction. So if we do the difference between these two, I get 13.828 newtons west is equal to 2 kilograms multiplied by my acceleration in the x direction. Dividing both sides by 2 kilograms, we get an answer of 6.9 meters per second squared west as my acceleration on the box, or the brick, I guess, in this case. All right, so there we go. We've determined the acceleration of the brick. So in this lesson, we looked at the difference between kinetic friction, static friction. We introduced the idea of limiting static friction, and we came up with some algebraic representations of how I calculate the magnitude of friction. All right, so if you have any questions or concerns about this lesson, please do not hesitate to reach out to me.